Thanks so much, and thanks, of course, to all of the wonderful organizers for putting on such an amazing conference. It's the end of the day on a Thursday before the dinner, so I want to make this talk as fun as possible in reward to you all for still being here. And I feel the need to preface this talk by saying I'm a mathematician, because a lot of this is going to feel like physics. And so you might, we can all be out of our comfort zone together, but that's okay. It's part of the journey. So I'm going to start with physics, go to mathematics, and then back to, and my specialty is moduli spaces, and I put a paper on the archive this week on moduli stacks. So that's where I come from. Those of you who know me already know this, but just, if you don't know me and you see the start of the talk, you're like, this is physics. Okay, but I'm taking this journey with you. That's my assurance to you. And the first thing I absolutely want to say is happy birthday, of course, to Yael, Lisa, and Jonathan. So Bill was trying to remember earlier where he first met people. So that got me thinking where I first met people. So, I think I met, Lisa was my postdoctoral supervisor, so I guess I have to remember that, obviously. So I first met Lisa in Toronto around 2010. Yael, the following year when I started here, one of the first people I met. First thing you told me was I was going to speak in the symplectic seminar, so there you go, and I did. And Jonathan I didn't meet until about, of course I knew him by reputation, as the amazing mathematician he is, but first met him actually in Canada, but not in Toronto. It was in 2014 in Halifax, one of my favorite cities in Canada, produces amazing people like Peter. It was actually a really, really nice session in honor of Bill. So, and I left that session with a homework problem from Jonathan that turned into two papers, which were both with Lisa. The first one was with Paul. I don't think Paul's around now, Paul Selleck, and the second one was with Jacques, who's here. So, but I'm not going to talk about that work at all. And the way we're going to start is not going to talk about these three individuals at all, at least to start. Instead, I'm going to talk about these three people to begin with. So this is slightly less impressive than a birthday, but a Nobel Prize. Okay, so the start of this journey, at least for me, was the news in 2016 about a Nobel Prize in physics for these three individuals, Thouless, who's now passed away, unfortunately, Haldane and Kosterlitz, so it says at the bottom here, for theoretical discoveries of topological phase transitions and topological phases of matter. So as someone who professes to do some kind of topology, at least 50% of the time, I thought it'd be nice to know what this was about. So that was the start of things. So here, by the way, is the Nobel Prize Committee trying to explain to the audience about topology by tearing apart pastries. I think the first thing they need to learn, though, is how to spell. But it's close, I guess. So what is this all about? And this is, I have to say, this is a big deal in condensed matter or solid state physics. So here's an article, a news article from Nature in 2019, strange topological materials popping up everywhere physicists look. And one of the key things about this picture, this is a very macroscopic picture in that you can see with your naked eye structure here, but you can probably see these honeycombs. And that's also a big feature of these materials, some sort of periodicity. So I guess to start, for us, I would love to be able to give you definition. Topological material is this, or topological materials are a kind of quantum material, quantum matter. I'd love to say definition, quantum matter, quantum material is this. But I don't really think there is a universal definition. It's one of these things often in physics that you kind of feel out. Quantum materials are maybe best defined by what they're not. They're materials that have behaviors with no counterpart in the usual macroscopic world of materials. Their behaviors are described as emergent ones, resulting from some atypical dependence of four parameters. You can imagine that materials in general occupy a moduli space with 4 coordinates called charge, spin, orbit, and lattice, which doesn't really matter what they are, but that usually these 4 things, these 4 parameters are independent, but sometimes they develop dependencies, and when they do, weird things happen. And then the material becomes a so-called quantum material, of which the topological materials are just an example. So this dependence that I mentioned is maybe induced sometimes under very precise or extreme conditions. So in the last Blitz talk, we heard about the quantum Hall effect, which is a great thing to study if you're interested in condensed matter or in solid state physics. And there, the condition that, so there's a dependence of charge or resistivity, of conductance or resistivity on a magnetic field that becomes discretized, quantized, that is unexpected. And this happens at very, very low temperatures in the presence of a very strong transverse magnetic field. So this is examples of what I mean by precise or extreme conditions. So very, very thin, highly crystalline films, supercooling, strong magnetic fields. These will sometimes cause materials to behave in ways that they shouldn't, but sometimes these are very profitable sort of behaviors to try and leverage. Okay. So I don't have a definition for you other than this. Some people will say strongly correlated systems of electrons, but then you have to define what that means. Okay. So let's go with this. Let me try and give you some examples. Okay. Again, this does not sound like mathematics, but it's a place to start, and we'll get there. So spin liquids are an example of quantum materials. These are crystalline materials in which the constituents are very nicely ordered in a regular pattern, but the spin of the atoms are disordered and dynamically fluctuating, which is more like a liquid. So this is a solid that behaves like a liquid. Weird. Okay, that's an example of a quantum material. And I can give you a real life example. Yttrium titanium oxide, which is an example of a titanate pyrochlore, is a common example. Spin glasses. So these are materials that are magnetic, which would suggest that the spins of the atoms are very highly ordered, but in fact they're completely random. So a spin glass. Glass, you'd expect that things are arranged more randomly. So iridium, manganese, gallium is an example. Again, under the right conditions. Topological materials, that was what we heard about in that banner about the Nobel Prize. So these are materials in which the topology of the energy spectrum, we'll get to that, enables some global conductivity features that differ from local ones. So these are materials that have a conductivity property that's different in a global sense than in a local sense, which is unusual. So sometimes there's an effect on the boundary of the material that isn't happening on the bulk of the material. The most prominent example of these are the topological insulators, in which the material is an insulator in its bulk, but a conductor along its edge or surface. So examples of these in 2 dimensions are mercury telluride sandwiched in cadmium telluride. So 2D means for the physicist or a thin film. For us, it means, you can think of it as the plane. In 3D, bismuth antimony. And it was the theoretical prediction of these combined with the experimental realization that got those 3 folks their Nobel Prize. There's even a kind of algebra topological classification of topological materials. So this is due to Kitaev. And then this is taken much further in recent years by people like Dan Freed and Mike Hopkins, Theo Johnson-Freud, Kapushtin. It's a great story, which I'm not going to tell you anything about. I'm going to go in a different direction. Okay, so they try to extend this table in very nice ways. I'm going to go in a different direction that introduces more geometry into the situation. But first, we need to talk about the origin of topology in this condensed matter story. And I would say that the origin is really periodicity, which was something I was emphasizing when you saw those honeycombs. So, you can think about the sort of material science or chemical basis of materials in terms of these 2 pictures. One is crystalline, and the other one is amorphous. What's interesting about, and things basically come in, there's polycrystalline in between, but basically things come in these types of extremes. Things are either nicely organized or they're not. And what's interesting about this is that locally, these 2 things are the same. So this is silicon dioxide. You have a silicon atom with 2 oxygen atoms attached, and locally, these 2 things are exactly the same. But you can tell that from a standing back that they're different. So the interesting pop quiz. Does anyone know what these 2 things are? I told you it's silicon dioxide, but does anyone know in common parlance what these are? Yeah. I mean, this is sand or glass, and this one is quartz. Okay? So quartz is the crystalline one, and this has a lot of structure, and this one has a nice optical property, you know, you can see through it, but it's more brittle than this, which has a lot more rigidity. And you know, this says that it doesn't. This is a good demonstration, what I just said, of the fact that it's not just the ingredients that matters, it's the geometry of how they're arranged that matters as well. Okay? So it's not just the ingredients you put in. You can take all the ingredients for a cake, but you can make a disaster out of them. Okay? So it's the same thing here. So what we're going to focus on are nice regular arrangements like this. So lattices in some dimension. And we're actually going to stick to two-dimensional lattices. So materials with a two-dimensional materials. So for us, that means R2 with some lattice on them. Okay? So crystal means lattice, 2D material means R2. And we're going to introduce a periodic potential that remembers the crystal or lattice. So this is some invariant function V, real valued, that looks the same. So invariant here meaning it just looks the same in every cell. You could say that's invariant under the action of the translation group of the lattice. And you could ask, is this a reasonable physical thing to do? Perhaps so. In a regular crystal or lattice, you know, you can't distinguish any two cells, so there's no reason for the potential to desymmetrize the picture. You'd expect that just in some material that's given to you that's very regular, that everything is regular about it. You know, there's no need for the potential to have some strange asymmetry. Well, what makes this whole thing quantum, we're going to take this as already being quantized. So we're going to think about electrons propagating on this lattice, really propagating in R2, but in a way that respects the lattice. And this is described quantum mechanically by the eigenvalue problem for this Hamiltonian, which is the Laplacian or minus the Laplacian plus this invariant function that we chose earlier. Again, invariant with respect to translation of the lattice. And this is a sort of continuous or smooth way, if you like, of building a model for this, as opposed to, so here it's like we took R2, and the way we're creating the lattice is by taking this V, which has the invariance of a translation group. The other thing that you could do that is very common in condensed matter is to start with the lattice and then build the Hamiltonian term by term through nearest neighbor interactions, which is a more discrete version of this. But this is what we'll look at. Standard Euclidean metric, yeah, at the moment, exactly. So this non-compact periodic medium, so R2 with this lattice, you could replace it with a compact but topologically non-trivial domain, of course, which is just the quotient of R2 by the lattice group. And that's fine. But you could ask the question, you know, do the solutions to the eigenvalue problem, which is, again, really time-independent Schrodinger's, can this be expressed in a reasonable way on the compact domain? In other words, are the solutions to this eigenvalue problem invariant under the group? And the answer, generally speaking, is no. However, the solutions are not too far off from being periodic in a particular sense. And this is due to an old theorem that's almost 100 years old of Bloch, that says that solutions for an invariant potential can be written in a basis of quasi-invariant solutions, which I'll tell you what this means. But I also want to say that this is not say Spencer Bloch. Okay, this is Felix Bloch. Okay, so this is the physicist Bloch. Okay. And this is really a mathematical theorem. You can think about it as a representation theoretic theorem or a theorem about PDEs, either way. But I guess you know, every third year physics student who takes a condensed matter course will learn about this theorem and probably prove it incorrectly. But math students will never hear about it, usually, in any phase of education. But that's fine. So just to make the ideas here a little bit more precise, so again, we're considering R2, let's say with a parallelogram lattice. We're going to identify this with its translation group, it's really Z cross Z. And I'm going to pick some cell to be the fundamental cell. It doesn't matter which. So I'm thinking of a picture like this. This is my crystal. It's just R2 with this lattice. And the important thing is that the eigenvectors of our Hamiltonian are really functions that look like this. So just to unpack this, you could think about this part right here as being defined on the fundamental cell. So this is a solution that is corresponds to an eigenvalue. There's a discrete spectrum. You can say that you have a 0th eigenvalue. They're bounded below. You have a 0th eigenvalue of first, second, third, and for that particular eigenvalue, this is unique after the choice of a good boundary condition on that fundamental cell. Now, when I try to extend this to further cells, which I can think of as the action of the translation group, you pick up. It doesn't just extend in a fully invariant way as when I translate x by lambda, it's just the same as x in the original cell. It picks up this additional u1 valued function or phase factor that contains a term here, a function here that depends on your choice of lambda. So this k here is a function from z cross z. It's a representation of z cross z into the circle. And so, and there's nothing actually in the differential equation that specifies what this k should be. In other words, the boundary conditions are not enough to determine which function k is here, so they're all possible. And so the collection of all of these quasi-periodic functions, which has a discrete direction coming from n, and then a sort of continuous direction coming from k, which is really the space of u1 characters for the group, these provide, what Bloch tells you is that these provides a basis for L2 functions on R2. And these are actually eigenvectors for the translation operator induced by lambda, but that translation operator is simultaneously diagonalizable with both the Laplacian and the potential, and hence with the Hamiltonian. So you can think about the Hamiltonian kind of diagonalizes in this basis, and as I was saying, the eigenvalues will depend on this choice of representation. And so just to maybe make this visual, this was sort of my fundamental solution for the nth eigenvalue, and then this is its transformation by this phase factor when I go to this neighboring cell. So Bloch's theorem gives us a description of the solutions in terms of data that depends only on the lattice, or equivalently in terms of data that depends on essentially the topology of an elliptic curve, because I had R2 and I modded out. I can mod out by a particular lattice now, or the lattice that I started with. That's some specific lattice. So this is really some elliptic curve, although it's not referred to like that in the condensed matter literature. It's just to them it's just some torus. Although the size of the lattice, and hence the specific elliptic curve, actually does enter the physics as the Hall viscosity is what it's called there. But in any case, this is, if you like, the effective space where the electrons are propagating. You just need to know what's happening on the fundamental cell, hence this elliptic curve, and we know how to generate the rest of the solution or the wave function through these phase factors. And these functions k, of course, are just abelian characters of the group. If you like, they live in the dual elliptic curve, or the Jacobian. So really, this is where the electrons were propagating, but we're going to work here instead. And this is now a story about two tori, or two elliptic curves. I have the position space, or the real space. This is the effective space where the electrons propagate. This is where the representations k live, these abelian representations. The physicists would say that this is the momentum space, or it's the Brion zone. Okay, if you want to be extra fancy. It's also, again, this is really an elliptic curve, and it's dual. And what I can do is, remember, this is the space of k's, so I can choose a k here, and then I can plot the discrete spectrum above this k, and it's changing as I change k. And this is a really, really important feature of the condensed matter, this whole condensed matter story. In fact, what I'm going to do is let's choose a little interval, if you like, somewhere in this torus. So I might get a picture that looks like this, and there's essentially two types of pictures here. So here's a few k values parameterized in some way, and I could think about these as the sort of sheets of the spectrum. These are maybe another thing I should say is that I should think about this as a kind of theory of orbitals associated to a whole material. Individual atoms have orbitals. There's a spectrum associated to it. You should think about this as now an emergent spectrum, that varies with this k associated to the whole material. And so I could think about electrons propagating as occupying these levels. So I could think about here are all the levels that are occupied at the moment, and this is the highest occupied level, and these are the unoccupied ones. So this is a partitioning of the levels into two sets. The conduction band and the valence band is how it's usually called. Another thing you could do is just think that there's two levels, consider what's called a tight binding model. I just think about the lowest level and the next one, and then I can just really think about, instead of grouping these, I could think about this as just one level, the lowest level, the next level, and I don't care about any other levels. I say that I don't have enough energy to reach those. So these are just two kind of ways of rationalizing this picture mathematically. And then this value mu is called the electrochemical potential, or the Fermi level. And this is determined by the actual atomic components. This part is not mathematical. This part is determined by the material. And this is like a high jump bar. And so the difference between these two pictures is that here I have a gap that's squarely around mu, and here mu passes between the two types of sheets. And this is the difference in mathematical terms between an insulator and a metal. And this is a mathematical way of understanding from the spectrum what an insulator is and what a metal is. So this can conduct. Here things have enough energy to jump from one side to the other, and here they don't. And so this is a coarse way mathematically of telling the difference between these two basic types of solids. Okay? And so this is a fascinating thing in my opinion, but it's actually just bread and butter. Daniel. Well, there's nothing in between. These are discrete levels that are separated.
What if you have tangents?
Oh, like if mu touches. Yeah. Okay, these kinds of things are very interesting. That's a very good question. And so we could get into that. There's various kinds of degeneracies, Weyl nodes, Fermi nodes, and these have meaning. I'll just say that that's a good question, and it has physical meaning. And you could go into that, and people spend a lifetime studying that. So yes, absolutely. Okay, and just to inject some reality, here's a real material. Here's silicon, and this is its band gap here. So this is K. These are the energy levels, and so people can draw real pictures from these after measurements of the spectrum of the material. So this is just to convince you that there are real people really know these things for common materials. But of course, this picture, even for silicon, you have a torus, a two-dimensional torus, or a one complex dimensional Jacobian, and what you're seeing here is just some sampling along some trajectory. If you stand back from this and try and form a more realistic picture, you might get something that looks like this. Okay, so you have one type of band here, another type of band here, and here's the potential. And here's some crossing points, by the way, because you can get branching. This is really a branched cover of the torus. If you pull back even further, what you get are actual surfaces of some genus. So this is some you have some branched cover of your torus. The branching induces some higher genus, and you could ask whether these are just surfaces or whether they're Riemann surfaces. And in at least the nicest cases, these actually come with a complex structure. And so this is a famous paper in the condensed matter world from 1993 about the Riemann surface of the Bloch function. So these are actual branched Riemann surface covers of the Jacobian of the elliptic curve that you started with. So there's actually really nice geometry here. It's just not usually thought of in this way. And the Chern class of this branched cover, if you think about the tangent bundle or if you like the canonical or anti-canonical line bundles of this cover, and you look at its Chern class, this is an invariant that's related to an invariant that appears in the condensed matter literature, which is the TKNN invariant. And Thouless was one of the 3 Nobel Prize winners we saw. And this can actually give you a nice interpretation of the numbers that appear in the quantum Hall effect that was referred to already. So the point is that there are invariants actually I guess my point at this stage is that there are invariants that appear in condensed matter literature actually for a long time that have a nice interpretation in the way we think about geometry and topology. These are really Chern classes of things. And so if you want to build a dictionary now between between the physics here and the math. So you have this effective position space where the electrons are propagating. That's some elliptic curve. The momentum space of the Brion zone is its dual curve of the Jacobian. There's a position momentum duality. You can Fourier transform going back and forth between, I guess you could say, x coordinates and k coordinates. But this is, in algebrogeometric terms, is the Abel-Jacobi map after a choice of base point in the elliptic curve. The band structure, which is again this set of sheets and their relation to the electrochemical potential, mu, this forms a branched cover of the Jacobian. And then the band invariants, which are sort of finer features of the band structure, are really corresponding to the genus and the Chern classes, which of course are related by Riemann-Hurwitz. And then maybe I'll also say something. I just want to go back to these pictures. So these sheets, they live in some ambient bundle of Hilbert spaces, that's over the Jacobian. And this bundle may be non-trivial, which is the first thing that we might think about. But for a long time in the condensed matter literature, there was no attention paid to whether the ambient bundle here was trivial or not. If this bundle is non-trivial, if it has a non-trivial, say, Chern class, then that's what opens the door to what are called topological materials that have these global conductivity features that differ from local ones. So that's a crucial piece of the story if you want to understand about topological materials. But it just comes down to the observation that the background bundle of Hilbert spaces, which you can take to be finite dimensional if you think about, again, what I call tight binding, that bundle may be non-trivial. And that is an important feature which was not really observed before people like Thouless, who has that invariant named after him and who's one of the Nobel Prize winners. Okay, so a naive question, a game we can play. Can the position space, like I said, one game has been played by people like Fried and Hopkins, and they've tried to push this theory of topological materials into greater generality, often involving working in arbitrary dimension. But let me ask you, let's stick with 2 dimensions. There's no reason to leave it behind. Can the position space be a curve or a Riemann surface of genus G bigger than 1? So I think that's a reasonable question, kind of question a mathematician would ask. But then to understand whether there's a reasonable or sensible answer to this, we have to remember where our position torus came from. It came from taking R2 and modding out by that lattice. And then if we do, fit something like this here, then the next question will be what goes here. So to produce a genus G greater than 1 position space, well, we need a lattice or a tiling or a tessellation with a higher gonality, a larger number of sides. For example, if you want genus 2, then as we know, we need to tile by octagons. If you want genus G in general, then you should tile by 4 G-gons. So, but we also know that you can't do this well in Euclidean space. So now, to connect with what Yael asked at the very beginning, we ought to change the metric and work on hyperbolic space. So here's, of course, a tessellation of hyperbolic of the Poincaré disk by octagons, Poincaré regular octagons, and then if you've never done this before, but you should try it. You should take it'll frustrate you, but you should take some piece of material and try to cut out an octagon, try to identify opposite sides, and check that you get this. There's a 10-minute video on YouTube set to Tchaikovsky where they do the folding very slowly. It's very hypnotic, and if you have 10 minutes to spare, you should watch it. Okay. The key thing now is that we're going to choose again a periodic potential. But what does that mean? It's something that's invariant with respect to the translation group, which is a Fuchsian group, so if you like a discrete subgroup of SU11. But the point is this is also now non-abelian. And so the first thing you should think about when that happens is like, am I, at some point higher rank representations are going to appear, and they certainly are. And now, what is our Schrodinger problem? What is our eigenvalue problem? So it's essentially the same thing, but I'm going to replace the Laplacian now with the Laplace-Beltrami operator. just given that we're in hyperbolic space now. And the question might be, can we solve the eigenvalue problem can we solve the eigenvalue problem? And so this is not my style of thinking, but I got to a stage in this where I started working with people from condensed matter physics. And they jumped to, let's do something numerically, and let's work with finitely many cells. And I say, okay, sure. And I said, we kind of want to do this in a global way on the whole disk. And I said, no, but we're never going to ever engineer that. You're only ever going to build finitely many cells. And I said, okay, sure, why not? Okay, so just let's take one cell. And this is a particularly nice choice. This is the Boltzmann octagon, which gives you the Boltzmann lattice, which gives you the Boltzmann surface when you quotient by its translation group. Its translation group is discrete with 4 generators, which are pictured here, R, U, S, and T. So there's these 2 rotations, and then there's 2 reflections. And what we did was, and this was sort of new to me, take this octagon and triangulate it into many, many triangles, and then use software to solve the eigenvalue problem numerically on the fundamental cell. And you get a solution. This allows you even to include boundary conditions. And then we started going to some neighboring cells and putting in U1 valued phase factors for this particular Fuchsian group. And what we did was we actually numerically computed the spectrum. So this is in k coordinates that goes with, well, in this case, we actually just took v equal to 0, which is of course invariant. And what we did was we plotted the spectrum, as you change this choice of representation k. So here we have this fixed solution, and then going out to these cells, we had to pick, you have to pick some k's. And so here's a 1-parameter family of k. We picked one, and then that's k. We chose that to be k equal to 0 in our coordinates, and then we varied k in a kind of 1-parameter family, and we tracked numerically what happens to the spectrum. And so it got a picture that looked like this. You can see some degeneracies where points come together, but you can also see some things that look like gaps. These are what the actual wave functions corresponding to these eigenvalues look like. So here's the lowest eigenvalue, the next one, the next one, the next one. And so this is a sort of color plot of the fundamental solution corresponding to those first 4 eigenvalues. So these are the wave functions in a color plot, and this is the modulus squared of the wave function. And then we turned on a non-zero potential, which is an approximation to a particular Eisenstein series. So again, we really have to work with in a more automorphic way now than before. And then so the red curves here are so you can see the old spectrum when v was 0, and now you can see the new spectrum and how it perturbs from the old one. And here's the updated sort of moduli square of the corresponding wave functions. So the point is that you can do some actually nice computations here. So this is coming from looking at one ring around the central cell in a hyperbolic lattice. And so my co-author Joseph Pacheco for this he's a condensed matter theorist, and this was the first paper we wrote, and it's called Hyperbolic Band Theory. So it was an attempt to do this electronic band theory, but for hyperbolic geometries. And something that we found, which kind of expected at the beginning, is that you could go out to a larger number of cells, and you could look at these numerical solutions. You could look at these choices of phase factors, and you could actually plug them back into the original eigenvalue problem, and then look at the error. And we see that the error was responsive to including more cells, but the error is also responsive to introducing higher order representations. There were sort of errors that we couldn't get around, but as expected, because we're dealing with a non-abelian group, you really do have to consider higher rank representations now and include those in your Bloch basis. So the suggestion here from the experiments is that all possible ranks of the phase factors are necessary now as the number of cells start to fill the hyperbolic plane. And what that really means is that there's infinitely many of these Brion zones or momentum spaces for a single material, one for each rank. These are really character varieties. We're talking about UR character varieties now for the group. And remember, this is just like we really are dealing with an elliptic curve in the old story. We're dealing with some actual Riemann surface here. And there is a complex structure that's inherited that recasts these as moduli spaces of stable holomorphic bundles. So there's a few things I want to advertise here, so I'm not going to go into too much detail, but there's a follow-up paper that I wrote with Joseph where we talk about the higher, this sort of higher or hyperbolic Bloch theorem, where you include these higher rank representations in PNAS. This is, I would call, the physics paper. And then with a student of mine, Elliot Kienzl, and with a collaborator of mine in mathematics, Akash Nagi, we wrote sort of two math papers here, which kind of make this. So this was the paper with Joseph and PNAS, automorphic Bloch theorems. But then the math papers, so this is the paper with Elliot, and it's the paper with Akash on the hyperbolic Bloch transform, where we try to make sense of this in a rigorous way. But the answer here to, okay, you can put a genus G surface here if your electrons are propagating on a hyperbolic lattice. You don't find hyperbolic lattices in nature, but that's a different story. But if you had one, the space of momenta, or whatever you want to call this, is now disconnected. And here's the Jacobian again, the abelian Brion zone. Here's the U2 representations, the U3 representations, and so on. And so the interesting thing about this is now you have a band structure over here that's a branch cover of this, but you also have a band structure here and a band structure here. And so you actually have countably many band structures, which all contribute to the overall behavior of the material. So it's much more complicated than a Euclidean topological material. And you can think about these as somehow infinitesimal corrections to the bulk behavior that appears here. But if you really, for extreme purposes like quantum computing, if you need to have a very precise behavior of a material, you might want to try and fine-tune the band structure in this regime. So this is already somehow quite a new perspective. And something, classical fact from Narasimhan and Ramanan is that if we used octagons and we have a surface of genus 2, then the rank 2 Brion zone, so that first non-abelian component, is homeomorphic to CP3. But in general, these are compact, but typically singular, because these are moduli spaces of bundles of degree 0, and 0 is not co-prime to the rank. So in general, these have singularities. And as I was saying, the higher rank things can be treated as infinitesimal corrections to the Bloch data. So there's a few implications of this, that hyperbolic materials, you can think of them as well, they kind of come with a moduli space, a 3G minus 3-dimensional complex moduli space with just the moduli space of Riemann surfaces. And coordinates on this moduli space can be thought about as maybe algebrogeometric invariance of the materials, material invariance that we didn't see before. The rank of the representations or of stable bundles, however you want to look at this, on either side of Narasimhan and Seshadri, is disconnecting the momentum space, as I emphasized in the pictures, and gives you infinitely many band structures to play around with. You can compactify this moduli space, which may lead to materials with enhanced symmetries or degeneracies. I'm just saying that now that this is fully geometric, there's geometric considerations that might have physical implications. There's a geometric playground here that wasn't there before. I won't say much about this. I'm just commenting on the fact that just a bit of musing on the Abel-Jacobi map, but I think I'll leave that and just focus on some other things. You can be sort of very concrete in the sense that if you have if your position curve, so hyperbolic plane mod gamma, happens to be hyperelliptic, well, then you know that it's a double cover of P1, and it's cut out by degree 2g plus 2 polynomial in an affine coordinate on P1. First of all, the hyperelliptic involution is a new symmetry of the material. You often talk about time reversal symmetry of these materials, but now you have a sort of space reversal symmetry. So that's an interesting thing to explore. And then the push forward to P1 of line bundles from your genus 2 position space, or if you like, line bundles in the Jacobian of your position space, produces not only a rank 2 vector bundle on P1, but also a Higgs field, which is going to be a linear map from this bundle to itself, but twisted by g+1 degree polynomials. So that's half of that. And the spectrum of this linear operator is precisely the position curve. So this is saying that, if you combine this, if you think a little bit more algebro-geometrically about this, not only do you have a spectrum of something living over the Jacobian, which is sort of the Bloch spectrum, the actual spectrum coming from Schrödinger, but the position curve is a spectrum of a linear operator, which is this Higgs field. And so there's two spectra going on at the same time. And then it leads to this picture. You've seen a lot of nice pictures in here, and I'm going to tell you who drew those. I drew these ones. I apologize. Okay. I have a student who's an amazing artist at the same time as being an amazing mathematician. But the picture that I was telling you is that, okay, suppose I have a genus 2 position space. Every genus 2 curve is hyperelliptic, and so it has to be a 2-to-1 cover in some way of P1. And then here I have this is a space of line bundles, space of stable rank 2 bundles, and so on. This is my Brion zone. And here's that hyperelliptic involution, that flips around the two sheets in this 2-to-1 cover. That's an interesting symmetry to think about physically. And this thing is embedded in the total space of a line bundle of degree g+1, as I was mentioning. And so what happens is if I pick a line bundle on here, which is equivalent to picking a point in here, and I push it forward, I get a rank 2 vector bundle down here, and I get this linear map from V to V tensor, a line bundle which is OG+1. It's the one whose sections are degree g+1 polynomials. But the interesting thing is, and this is kind of standard Higgs bundle Hitchin theory right here. But if I take a point, it's motivating us now, the physics is motivating us to do something different mathematically. What if I take something from here? That's a rank 2 bundle. That's supported on this. And I push it forward. I will get a rank 4 bundle. And I'll also get some sort of linear map here, which you can try to understand, for which this is the spectrum in some generalized sense instead of the ordinary sense. And you can play this game with rank 3, 4, and so on. And so actually Hitchin and Shaposhnik wrote a paper about this some time ago, I think 2013, non-abelianization of Higgs bundles. But this motivated me and a PhD student to think about this in a more general way. But this is a picture of the Hitchin fibration, of those of you who know about it. This is space of characteristic polynomials. And over each point, you have a copy of a Jacobian of some spectrum, some Riemann surface. So these surfaces are varying, and so these are varying, and this is keeping track of how those tori are varying. And this here would be the Hitchin fibration, but this is motivating us to consider what if you had a fiber that was disconnected and you had higher rank moduli spaces of bundles. So I explored this enhanced Hitchin moduli space with a student, Kuntal Banerjee, and we wrote a paper on this. It's kind of an extension of Shaposhnik, or Hitchin-Shaposhnik. But the point is, I would not have considered this if I were not thinking about hyperbolic matter. So this can be a source of inspiration in pure mathematics. So some math things to work on if people want projects. You can think about exact wave functions here. Can you extract the wave functions for the hyperbolic matter problem explicitly? One method is topological recursion, which is a recursive procedure that's put in motion by the choice of an integral kernel, like the Bergman kernel, which we just heard about. And so I wrote this turns, if you like, data of ordinary spectral curves into wave functions that solve exactly quantizations of those spectral curves. And this has some utility here, and I wrote a paper with my PhD student, Christopher Mahadio, who's now at UIC, about this. Understanding branched covers of moduli spaces of stable bundles is something that is kind of a high priority here. Again, looking at these band structures over these higher rank moduli spaces. Cataloging the new invariants of the condensed matter physics that you get from thinking about things geometrically. Thinking about all kinds of symmetries, extra special things that happen on the geometric side. What do they mean on the physical side? I just have a suggestion here. You can also discretize this picture and then think about this instead of terms of Hitchin systems, think about this in terms of quiver varieties or Nakajima quiver varieties. And I speculate about this in my paper with Elliot Kienzle that I mentioned earlier. Okay, so just to finish off, I want to just to end on some fun notes. I want to tell you about some things that you can do if you had such matter in your hands. I told you, nature doesn't give you these things, but suppose you had. Can you program such matter? So you could think about the whole field of the emergent field of quantum computing as trying to turn matter, exotic matter, into computers. This maybe, and this has been a theme for today, I suppose. Well, yes, a hyperbolic band structure is a kind of qubit. Because it has a spectrum and it has discrete bands. And in a tight binding regime with two levels, it's a qubit, 0 and 1. But you can also regard the material as a gate. You have qubits and you have gates that transform them, logic gates. You can also regard, there's a kind of duality here. Instead of regarding the material as a qubit, you could regard it as a gate that transforms a signal that passes through it, according to parallel transport along a hyperbolic geodesic. You expect that a signal, the electrons are going to travel along a hyperbolic geodesic, and the lattice is going to transform that signal in a particular way. And this perspective can be framed as programming via compositions of two-dimensional cobordisms, which are position spaces in our story, but that also support flat connections. And so the idea is here, I have a Bloch sphere. This is my qubit. I have 0 and 1. Those are the two levels, if you like. And the idea is that a signal starts at some point in the material, ends somewhere else, and it's like a section of Bloch spheres. It's like a Bloch tube. I have some unitary state. So maybe this is unitary with respect to the Poincare metric. Maybe I have the Chern connection. Everything is nicely Hermitian, and I can just let the geometry of the surface take my initial state, whatever it was, and by parallel transport, send it to some unitary state over here. So this, in other words, the geometry of the effective position space is a kind of gate. And then you can think about composing these things. And so the rules here, this is the theme of the week. I'm really talking about a TQFT. Ever since Maxence started talking about these. So I wrote a paper with my student Mahmoud Azam called TQFTs in Quantum Computing, which is really all about how to program these materials. And so here are and these are TQFTs with enhancements. We have to keep track of geodesics in the cobordisms and flat connections and parallel transport operators along these. So this is a thickened TQFT. If you're interested, have a look. Can you simulate such matter? We don't have it in our hands. Yes, you can. You can do it with high performance computing. You can also go beyond that and use quantum computers, like this quantum computer in Quebec that we have access to. This is IBM Quantum System 1, which has 127 qubits, and we're doing exact simulations using variational quantum eigensolvers of the dynamics of this material. To prove that I have access to this, here I am. This is in Bromont, Quebec, outside Montreal in September 2023. And there are only 3 universities in Canada currently that have access to this machine. And there are only 3 of these available to universities in the world, 1 in Germany, 1 in Japan, and 1 in Canada. So this is exciting. And last thing, can you make such matter? Okay, nature doesn't give it to you. Can you make it? Yes. This is, looks like a circuit to you, a chip, whatever you want to call it. But don't think about it that way. Think about this as an approximation of a material. This is a synthetic hyperbolic lattice manufactured on a sapphire substrate using coplanar waveguides. It pushes not electrons, but photons around. And it does so in a way, in the tunings between the rings of coplanar waveguides, which are connected by resonators, are tuned in such a way to mimic the Poincare metric. And you see that signals propagate along what look like approximations to hyperbolic geodesics. So this was done by Alicia Collar and others at Princeton in 2019. This is from a Nature paper. They lamented the non-existence of a hyperbolic band theory, and then a few months later, our paper came out on hyperbolic band theory. So that was just a massive coincidence. The good is that this is a proof of concept for making these things. I told you there's good results about photonic signal propagation, and this has been the inspiration for, in combination with our work, for other experiments. This is a kind of tabletop experiment that tries to do the same thing. The difference is the prior thing I showed you is a superconducting device. Superconducting was run at about 10 Kelvin. But the bad is that there's, even at 10 Kelvin with the first one, there's high dissipation, very low signal to noise ratio. The device is still too warm, and in particular, there's no observation of the spectral gap. Our big prediction is a spectral gap, but they don't see that. So we had to take matters into our own hands. So this is something that my group is building together with a group at the University of Waterloo here in Canada, Institute for Quantum Computing. These are hyperbolic lattices. This is on a silicon substrate using, I would say, just a little bit more refinement in the nano engineering. So this is the lab we're working with is a lab that actually manufactures qubits of the style that are in IBM's machines or Google's machines in existing quantum computing hardware. So they're very good at manufacturing these kinds of devices. So we brought to them the idea of manufacturing our own hyperbolic lattices. And these devices run at 8, 9, or 10 millikelvin. Okay, so that's how cold this runs. And here you do have a chance of observing a spectrum. This is actually, so we have run signals through this device, and you get this is just it's called an S21 characterization, but this is not trying to look at the spectrum on the momentum space side, but kind of looking at just at signal propagation. But this is already very promising in terms of you wouldn't see these peaks in a Euclidean case. But anyway, we're actually building, if you like, components of quantum computers using these mathematical ideas. So that's and here's my student Tara in the lab at Institute for Quantum Computing, where she was learning. So she's a math student, a pure math student. But she is, having fun. She just came back from Waterloo a couple weeks ago. These are people I've worked with. This was Joseph. This is Alicia Collar. And then some of the students who've been involved. This is Mahmoud Azam, who wrote the TQFT's paper with me. I also have Matt Coben in the room, who's working on moduli, spaces, and stacks of quivers. But you're not immune to this, Matt. We'll get you into this very shortly. Secretly, you're going to be working on this soon. And these amazing drawings that you saw were all done by Elliot Kienzl, my former student who's now at Berkeley, used to be at Maryland, and he prefers, I think, this avatar. And these are our funders. Getting into hardware means you really need to have funding. These are our industry partners, in particular IBM, as you saw. Pink is the organization in Quebec that helps us access the IBM machine. We also have SWAG, my research center, turning math into this. So I hope you can see that we started with this, but the kind of math at the end of the day is the math of these folks here. So again, happy birthday, Yael, Lisa, and Jonathan, and that's a wrap. Thank you so much.